Hi, Abdul. I'll just share my screen, then we can start. I have allowed your microphone in case you want to respond to any of the questions. All right. Hello, everyone. Welcome to the 11th weekly discussion and doubt clearing session of the NPTEL course on concrete technology, NOC24-CE46, which is taken by Professor B. Bhattacharjee of IIT Delhi. I am Ashirvad Satpathy. I'm a PMRF Research Scholar of IIT Delhi. What I do is I take these weekly sessions of 2 hours where we discuss the assignment questions of the previous weeks, which you have already submitted the answers to. And we also take up any doubts that you might be having regarding the previous week's lectures. There is another teaching assistant to this course. His name is Debojyoti. He usually takes his weekly sessions of 2 hours on Saturdays from 6 to 8 p.m. And I take my weekly sessions on Mondays from 6 to 8 p.m. In today's session, we'll be discussing the week 10 assignment 10 questions. There are around 10 questions which are related to durability aspects of cement and concrete, meaning the different processes that affect the durability or the lifespan of a given cement or concrete structure. And they included the corrosion reactions arising out of carbonation or chloride, then alkali silica reaction or alkali aggregate reactions. Sulfate attack was also discussed with you, and these assignment 10 questions are related to those concepts of the lecture. At the end of the session, we will also take any doubts that you might be having regarding the week 10 lectures. So the first question in this assignment was durability of structure, component, etc. is its capability to maintain a dash performance level over a specified time when exposed to degradation environment. So you have to fill in the blank. Durability of a structure depends on dash performance level over a specified time when exposed to degradation environment. Is it maximum performance level, minimum performance level, constant performance level, none of the above, and why? Yes, yes, Abdul, go ahead. Um, if you're trying to say something, I'm not able to hear you. Am I audible to you, Abdul? Can you just respond in the chat or give me a thumbs up or something? Am I audible to you? Because I am not able to hear you. Let me just check my audio settings. Abdul, are you able to hear me? Yeah, my microphone is working and my speakers are also working fine, I guess. Could you try rejoining the meeting? You could exit now and then rejoin. There could be some issue with your, yeah.
Is it here
Yeah, yeah,
audible, sir?
yeah, you're audible
Oh,
now.
oh,
Go ahead.
okay, that answer is minimum performance, sir.
Minimum performance level. Why would you say that?
That is according to the standard specification and all this. It is mentioned like that.
Yeah, okay. So thank you, Abdul. That's the correct answer actually. It is minimum performance level. Just give me a moment. So it is the minimum performance level. Whenever we discuss or try to describe a given parameter of a performance of a structure, let's say, be it strength or durability against fire, or durability against corrosion, or the design lifespan of a structure. We always mention minimum values that the structure should be able to uh, perform till that value at least, so that we are in the safe zone. We maintain safety for the residents or for the structure itself as well. Likewise, in the case of strength, as I mentioned, when we talk about characteristic compressive strength of a structure, we use words like at least. It should at least 95% of the results should exceed this value. So we use words like minimum performance level, or at least this 30 years lifespan of a structure. Or when we talk about durability against fire, let's say we rate our structures based on the R rating of a given element, meaning that uh, a given beam or a given structural element should be able to sustain a fire of this degree till at least 3 hours or at least 4 hours. So we use these kinds of minimum criteria, minimum or at least. These words are used. The qualifying these mention the qualifying criteria for a structural element or or a material itself to be able to provide us with acceptable performance. Provide acceptable performance, right? This is the answer to this question is durability of a structure is its capability to maintain uh, minimum performance level over a specified time. Again, the keyword over here is specified time. You have to mention the time in which you want this performance level to be maintained. And the second most important parameter of it is exposed to a certain degradation environment. Structure that is durable in one environment might not be durable in another environment. So you have to also specify the kind of environmental exposure that you are providing to the structure for it to qualify the degree of performance level that you're mentioning, right? So this is the correct answer to the question. Moving on to the second question, it is an assertion and reasoning kind of a question. The assertion here mentions that magnesium sulfate ingress is more dangerous than sodium and potassium sulfate ingress. And the reason that they have mentioned is CSH is not stable in the presence of magnesium hydroxide. So you have to answer if the assertion is true, if the reason is true, and if the reason is the correct explanation of the assertion or not. The assertion here, I'll repeat, magnesium sulfate ingress is more dangerous than sodium and potassium sulfate ingress. And the reason they have given is CSH is not stable in the presence of magnesium hydroxide. Yes? Can you answer this question?
Yeah, question assertion and reasons are true, and reason is correct explanation of assertion.
Right, right.
Because this sulfate is in more. It is chemically it is more dangerous than sodium chloride. That is the reason what I'm thinking that way.
Mm-hmm. Thank you, Abdul. Yeah, that's the correct answer. But could you be more specific as how magnesium sulfate is more dangerous as compared to sodium and potassium sulfate ingress? Like, how does it affect the system chemically? You may, yeah,
I
you're correct.
that I think this a chemical action, if it is in the presence of magnesium sulfate, that it will make more deterioration for the concrete. I think deterioration will be more than sodium chloride.
All right. Okay. Yeah. Yeah. You're right, Abdul. The answer is correct. The assertion is true. That is, magnesium sulfate is indeed more dangerous than sodium and potassium sulfate ingress. And the reason is that CSH is not stable when in the presence of magnesium hydroxide. So when magnesium sulfate ingress occurs inside cement or concrete, it produces magnesium hydroxide. The magnesium sulfate, the magnesium and the sulfate ions react with the OH minus ions, that is the hydroxyl ions inside the concrete coming from the pore water, and they precipitate magnesium hydroxide, which we call brucite, right? This is magnesium hydroxide is brucite. This goes as MgOH whole twice. And brucite is an insoluble material. Insoluble material. If we compare this with sodium and potassium sulfate ingress, when they come in contact with the pore water, the sodium and potassium ions react with the hydroxyl ions, and they could release Na2SO4 or K2SO4, right? But these sulfates are soluble in water, soluble in pore water. And we also know that sodium sulfate and potassium sulfate um, are also present as impurities in the cement or clinker itself. So these types of alkali sulfates are soluble in pore solution. Now, when a alkali sulfate or alkali is soluble in the pore solution, it maintains the pH at a higher level. So we want, in order that the cement hydration reactions progress in a certain manner, the pH of the pore solution has to be maintained at a high level of the order of 12 to 13 pH, right? When you when the sulfate or the alkali or alkaline earth sulfates are present inside the pore solution and they react with the hydroxyl ions, as in the case of magnesium sulfate, they, it produces magnesium hydroxide that is insoluble in the pore solution, and due to that, the magnesium hydroxide gets precipitated, brucite is precipitated inside the cementitious matrix, and the pH decreases. So, due to its insolubility, the pH decreases. And when the pH decreases, the CSH is not stable. It wants to release its calcium ions because the alkali content, the reserve alkalinity in the system is now reduced. So someone has to contribute their alkaline elements in order to maintain that pH. So we call it the decalcification of the CSH. So the CSH tries to release its calcium ions into the solution in order to maintain the pH, in order to continue the hydration reactions. So CSH is not stable at low pH, and this low pH is, this low pH conditions are created due to brucite precipitation coming from the magnesium sulfate. So magnesium sulfate is in fact more dangerous than sodium and potassium sulfate ingress, right? So this is the correct answer to the question. Assertion and reason are both true, and the reason is the correct explanation of the assertion. CSH is not stable in the presence of brucite. So this is actually the mechanism how magnesium sulfate ingress is more dangerous. All right. Moving to the third question. To improve resistance against sulfate attack, which of the following is reduced in the cement? C3S, C2S, C3A, calcium sulfate, CaSO4. This is A light, this is B light, this is aluminate, and this is calcium sulfate. Yes, which of this is the correct answer? To improve the resistance against sulfate attack, which of the following is reduced? Which of the following phases is put in reduced amounts in the cement?
That is aluminate. Aluminate, it is reducing the improve resistance against sulfate. That's why
Right,
that cement also using sulfur resistant cement because of this case it is
right.
using. It's,
Yeah,
sulfur. But normally, if there is the air, especially for the underground structure and all these things, if the soil is sulfate content, then
mm-hmm.
sulfur resistant cement is recommending for in such condition,
Right.
isn't it?
Yeah, right. And
That is a yeah, that is the answer. Answer C3A. That is the correct answer.
right. You're very right, Abdul. This is actually the correct answer. And in fact, in the case of sulfate-resistant cement, we do try to decrease the aluminate content. But would you be able to answer what happens when there is excess of aluminates and the concrete structure undergoes a sulfate attack? I mean, how does
So
aluminate affect the sulfate attack?
that is a deterioration for the concrete. Concrete, and what it is called. Some residues will form, and there is tendency for cracking and all this thing.
Right, right. Yeah. Thank you, Abdul. So you're right over here. C3A content is reduced in order to improve the resistance against sulfate attack, and this is exactly why sulfate resisting cements have low C3A content. The aluminate content is low. What happens when there is excess of aluminates and the concrete undergoes a sulfate attack? So usually the source of sulfates is from soils or water sources. From these sources, the sulfates come into the structures. So majorly in the case of foundations, structures which are indirectly in contact with the soil, or in the case of bridge piers, retaining walls, and so on. So whatever the structures that are in direct contact with source of sulfates like soil or water. So um, when this when the cement has a high aluminate content, and we do add some amount of gypsum in the cement as well. Now the aluminate and the gypsum at an early stage react to form ettringite. We have discussed this in the previous sessions as well, but I'll just highlight it again. So C3A plus gypsum plus water react early stage to form ettringite, right? And gypsum, as we know, is a source of sulfate initially. And this is early. By early stage, I mean that the concrete is in a fresh state. It is still plastic. It has a lot of voids. So whenever the gypsum is produced, since it is a crystalline material, it occupies a larger volume than the unhydrated cement itself. And when this ettringite is formed in an early stage, it contributes to strength, right? But what happens when there is excess of aluminates in the cement? So some of the aluminate has already reacted in the early stage itself, and it has produced ettringite, and the concrete is now stable. but there is still some unreacted C3A present inside the cement, and there is a sulfate attack. So this unreacted aluminate will react with the source of sulfate, the sulfate ions coming from the any type of attack. It could be from magnesium sulfate, sodium sulfate, potassium sulfate, doesn't matter. The sulfate ions react with this unreacted aluminate, and the water present in the pore solution after the concrete is hardened to produce ettringite. Now, when the concrete is already hardened, the porosity is already reduced. The concrete is not in a plastic state to accommodate any further increase in the volume. So, when this crystalline ettringite is formed at a later stage, it doesn't have sufficient space to expand, and therefore it exerts a tensile force inside the concrete, causing cracking. So, in order that the resistance of your concrete or cement has to be increased against sulfate attack, you need to ensure that there is not much unreacted aluminate present at a later stage in the concrete structure. And for that to happen, you need to ensure that from the cement production itself, the aluminate content is low in the cement. So this is the correct answer to the question. To improve the resistance against sulfate attack, which of the following is reduced in the cement? It is the aluminate content that is reduced, and therefore sulfate resisting cements have also contain low aluminate content in them. Right. Moving on to the fourth question: to reduce sulfate attack, which of these is favorable? And there are three statements over here: low aluminates, low water to cement ratio, and use of blended cement. Which of these is favorable and why? To reduce sulfate, I mean to reduce the effect of sulfate attack. Yes, can you answer this question?
Yeah, this answer low C3 aluminate, that is low aluminate, low water cement ratio, and use of blended cement. These are three are favorable to reduce sulfur attack, which is the answer is 1, 2, and 3.
Okay, you mean to say that all the statements are correct. Can you
And
also explain why? I mean, we have already discussed about low aluminates.
Low C3A, that means aluminate. That means in case that is sulfur resistance in that case.
Right.
Low C3A. Low water cement ratio means that water cement ratio is reduced, that the strength also will increase, and porosity also will
Right.
reduce.
Porosity. Yes.
Porosity. And the use of blended cement, that is just like a fly ash and other that workability will increase, and silica fume concrete and all these things is connected with those things. Blended cement, I mean, blended cement.
Yeah. Okay. Yeah, I'll explain the fact about blended cements also. Yeah. Thank you,
Okay.
Abdul. You're right in what you mentioned. All
Hmm.
the three statements are correct with respect to reducing sulfate attack in concrete. We have
Okay.
already discussed about low aluminates and how low aluminates can reduce the risk of sulfate attack. Then,
Yeah.
coming to low water to cement ratio. When you have low water to cement ratio, it means that you have a lower, essentially, you're lowering the porosity in the concrete itself. When there's low porosity, for sulfate attack to occur, the sulfate ions have to get inside the concrete. When the porosity is low, the pore connectivity is low, then the sulfate ions coming from the external sources like water or soil cannot get inside the concrete, and there will be a barrier coming from the pore structure refinement itself, and due to that, the risk of sulfate attack is also reduced. So low water to cement ratio is also the right answer. This is due to low aluminate. The answer was to restrict Ettringite formation at a later age, right? At a later age. And finally, use of blended cements. It is similar to what we discussed about water to cement ratio. As blended cements mean they contain clinker plus gypsum, which is OPC, and some SCM. It could be a one SCM or a combination of different HCMs. And
Excuse me, sir. Excuse me, sir. I am keeping fasting for 10 minutes. I won't be available in the online. Then after 10 minutes, I will be back to
yeah, no,
online.
not an issue.
Yeah.
I mean, anyway, I'm recording the session, so you can always check it out. Yeah,
I will catch the recorded session. This
yeah,
after 10 minutes, I will be back. Just I
yeah,
am breaking my fasting.
yeah. It's all right, Abdul. Go ahead.
Okay, sir.
Okay. Yeah. So I was talking about blended cements. Blended cements are a mixture of clinker, gypsum, and any SCM. It could be fly ash, slag, metacolin, and a combination of these as well, or limestone, as we have in the case of PLCs. So what happens in blended cement is the SCMs are finer materials. They have a very low fineness, and due to that, sorry, they have a very high fineness, and due to that, when the this blended cements samples get hydrated, these SCMs can take part in the reaction, and when they haven't reacted yet, they can contribute in blocking the pores. So it could so happen that the porosity, I mean, usually the porosity is reduced in the case of blended cements, but it has been also observed that even if the porosity increases by a bit as compared to that of OPC systems, the pore connectivity is reduced. So when the pore connectivity is reduced, the ions cannot move from one particular location to another location for it to react with the aluminates or any other material per se, and therefore this also reduces the risk of sulfate attack. So when you include this fine materials like SCMs, they refine the pore structure and therefore reduce the ingress of sulfate ions. Low porosity reduce sulfate ingress. This is also the same aspect of it. Um, Reduce the increase of sulfate ions, right? So all the three statements are correct with respect to reducing the sulfate attack. All right. When we talk about blended cements, and I also mentioned Portland limestone cement, we should be careful while when we say that use of blended cement can reduce the risk of sulfate attack. Yes, it can reduce the risk of sulfate attack, but sometimes when we use carbonates in our blended cements, like in the case of Portland limestone cement, PLC. So limestone is a source of carbonate, or when your aggregates contain carbonates, or in the case of limestone calcine clay cement, when sulfate attack occurs inside the in the concrete, and there is a presence of carbonates in the environment, it could lead to thaumasite formation. What is thaumasite? It is a hydrated calcium carbonate silicate. So calcium carbonate silicate hydrate, as we call it. So it is a very soft material. It is insoluble in water, and it makes the concrete soft, and the concrete loses its strength. So we want to reduce this risk of thaumasite formation in the concrete, and it usually is very rare. Thaumasite is formed at temperatures below 15 degrees Celsius. So it usually is very rare in the, at least in the Indian or tropical conditions. It is usually rare that thaumasite is produced. But even if we are using these cements in other areas which experience very low temperatures, we should be careful while using blended cements containing carbonates. This could be what to say, this could produce deleterious effects of thaumasite formation under sulfate attack. So yeah, that is just a piece of information. Anyway, moving to the fifth question: which of the following statement is true regarding reducing alkali silica reaction in concrete? There are five statements they have given. The first statement is prevention of moisture ingress. Statement 2 is use of non-reactive aggregates. Statement 3 is use of blended cements. 4 is use of lithium-based admixture. Use of cements with high sodium oxide content. Which of the following statements is true regarding reducing alkali silica reaction in concrete? Which of the statements are correct? Can anyone answer this question? Abdul is away for some time. Pavitra, would you be able to answer this question? Which of the following statements are correct with respect to reducing alkali silica reaction in concrete? Prevention of moisture ingress, use of reactive aggregates, use of blended cements, use of lithium-based admixture. Can we just start by discussing what is alkali silica reaction and how does it affect the durability of concrete? Yes, anyone? All right, let's discuss all these statements one by one. Before going there, what is alkali silica reaction? Essentially, when um, there are reactive aggregates present inside the concrete, and by reactive aggregates, I mean that the silica source in the aggregate is amorphous in nature. It is reactive silica, and therefore, as we know that the pH inside the concrete is alkaline, it is the pore solution of the concrete consists of different alkalis like sodium ions or potassium ions. So these alkalis um, get inside the reactive silica aggregates. They break these SiO-Si bonds of the silica aggregates and precipitate a alkali silica gel. It's a gel-like material, similar to that of CSH gel, but it has a very low density as compared to that of CSH gel. And therefore, when this silica gel is precipitated inside the alkali aggregates, it expands in nature, it expands in volume and creates the aggregates to crack. And when the aggregates crack, they lose the strength. And as we know, that when the concrete fails, it fails around the boundaries of the aggregates and not through the aggregates. The failure plane doesn't move through the aggregates. It generally moves around the boundaries of the aggregates through the interfacial transition zone. But when the aggregates lose their strength, ultimately the elastic modulus and the strength of the concrete is also reduced. And sometimes, since this alkali silica gel precipitates inside the concrete, they could cause expansion, and that expansion could lead to cracking inside the concrete. But this process is a very slow reaction, and I mean slow reacting process, and therefore it takes a lot of time to act, for these cracks to be actually visible on the surface of your concrete structures. So this is the mechanism of alkali silica reaction in concrete. The statement one says, if we prevent the moisture ingress inside the concrete, would we be able to reduce the alkali silica reaction? So yes, this is a correct statement. When we reduce the moisture ingress, for the ions, the alkali ions to get inside the reactive silica aggregates, to get inside the pores of these reactive silica aggregates, there has to be a presence of a medium in the concrete. It could be pore water, or it could be an external source of moisture or water, right? So if we prevent the moisture ingress inside the concrete, the alkalis, even if they're present inside the pore solution of in the pore solution of the concrete, they won't be able to travel into the I mean the reactive silica aggregates, and therefore there will be no precipitation of the alkali silica gel. So it won't pose a problem. So the first statement is also correct. If we prevent the moisture ingress, we could restrict the transport of alkalis into the silica aggregates. Now, how do you restrict the moisture ingress? There are a few ways you can do it. You either use very fine materials like supplementary cementitious materials, so that your overall porosity and pore connectivity is reduced. So even if there is moisture available inside the concrete, it won't be able to get inside. Or else you could use these hydrophobic agents in your concrete. Like you could use some integral compounds while mixing your concrete, so that your concrete becomes hydrophobic. Or else you could use some paints on your concrete structures in order to reduce the seepage or water ingress into your concrete. The second statement is use of non-reactive aggregates. Of course, yes, because the presence of reactive aggregates is the main source of alkali silica reaction. However, it is not the only source. It is generally the main source of alkali silica reaction. For alkali silica reaction to occur inside concrete, there has to be reactive silica. Correction. Sorry. Yeah, there has to be reactive silica inside the concrete. Then there has to be alkalis present in the concrete pore solution, and there has to be moisture. This combination leads to alkali silica reaction. So all these three, if all these three components are present, then only you'll be able to see. You could be able to see alkali silica reaction in concrete. Abdul, you have raised your hand. Do you have a question?
Yeah, I come back after break, sir.
Oh, all right.
So
Yeah.
just
That's all.
thank you. I participate.
Okay. Um, yeah, we were just discussing this fifth question. Which of this statement statements are true with respect to reducing the alkali silica reaction in concrete. So first is moisture ingress, prevention of moisture ingress, and I mentioned that when you restrict the moisture ingress in your concrete, you essentially are restricting the transport of alkali ions into the silica reactive silica aggregates, and when you restrict that their transport, the alkali silica gel is not precipitated, and there are no deleterious effects coming out of the presence of alkali silica reaction. Then there is use of non-reactive aggregates. When the aggregates are non-reactive, reactive silica is the main source. So when the aggregates are non-reactive, it will reduce the risk of alkali silica reaction. Use of blended cements. So what happens when you use the blended when you use blended cements, and how do they reduce the alkali silica reaction? Again, it is the same as similar to that of moisture ingress. You essentially are refining your pore structure, and therefore uh, the transport of ions within the concrete is restricted. So pore structure refinement reduces transport of alkalis. One more essential component for alkali silica reaction to occur is the presence of calcium. If calcium is not present inside the concrete, then the precipitation of alkali silica gel is restricted. Of ASR gel is restricted. And in the case of blended cements, the amorphous silica that is present in these SCMs, meaning like fly ash or slag or metacolin or silica fume, the amorphous silica present in these SCMs that reacts with the calcium hydroxide coming from the hydration reactions of the blended cements of the clinker. Sorry. So amorphous silica plus portlandite coming from the hydration of the clinker and produces additional CSH or cash in the concrete. Now, when the when the calcium hydroxide is consumed by these SCMs, the calcium ion concentration in the pore solution is reduced, and therefore it also reduces the risk of alkali silica reaction. So that is also one way how blended cements help reduce the risk of alkali silica reaction. The fourth statement here is use of lithium based admixture. What does lithium? So generally, in order to mitigate the risk of alkali silica reaction, we used lithium carbonate. I exactly don't remember the stoichiometry of it, so I'll just write it: lithium carbonate. I guess it is the Li3 plus lithium carbonate or lithium hydroxide. And what the lithium ion does, lithium based admixture do is they replace the alkalis, replace Na plus or K plus, the alkalis present in the ASR gel and makes the ASR gel soluble. When the ASR gel is soluble, now it won't be able to precipitate, and therefore there will be no expansion caused even when there is alkali silica reaction going on inside the concrete. So when you use this lithium based admixtures in your concrete, you're providing a source of lithium, and this lithium replaces the alkalis that are present in the ASR gel that is being formed as a product of the ASR reaction, and uh, this replacement of lithium makes the ASR gel soluble in pore solution. And when it is soluble, it won't create any expansion. So no expansion. So again, using lithium-based admixtures also reduces the risk of alkali-silica reaction. And the final statement was use of cements with high sodium oxide content. Now, this is a wrong statement because sodium oxide is a source of alkali, and that will in fact increase the risk of alkali silica reaction. Yes, sir. So as I mentioned in the beginning itself, for alkali silica reaction to occur, there has to be reactive silica, there has to be alkalis present inside the concrete, and there has to be sufficient amount of moisture for these ions to travel across the pores into the reactive aggregates. So if we use a high sodium oxide content, then there will be a high concentration of alkalis in the pore solution, and that will in fact increase the risk of ASR. So the correct statements are 1, 2, 3, and 4. Right? Moving on to the sixth question, volume increase related to freezing is 7%, 10%, 9%, 8%. This is a pretty straightforward question. This was probably discussed in your lecture as well.
Yeah, it is 9%, sir. This already
Right.
discussed.
Yeah. This is a pretty straightforward question. Yeah. The correct answer to this question is 9% volume increase when there is a freezing. So, as we know, that ice has a lower density as compared to water, and that is exactly why ice floats on your cold drinks. And even if so, because ice has a lower density than that of water, and when a material has a lower density, it will occupy a larger volume for the same mass. So yeah, so I mean, due to that, when there is a freezing and thawing action going on inside a concrete element, the pore solution, the water in the pore solution freezes at very low temperatures, and due to this freezing action, there's an expansion inside the pores, and that creates a stress. And when due to the subsequent thawing action, this water comes out of the pores and then occupies the smaller pores. And when there is a cyclic freezing and thawing going on, this causes a fatigue kind of an action in the concrete, and this leads to cracking of the concrete due to freeze thaw action. So yeah.
Actually, this pressure, I mean, this stress inside the concrete, that means it is only tensional force, isn't it? While expanding this water inside and it is getting the ice, that time that force is developing and the pressure is going to just like a tensional force, isn't
Right,
it? No?
exactly. Yes, it
Yeah,
is a
that's why.
tensile force. Whenever
Yeah,
something expands inside a very compact volume, it exerts a force on the boundaries in the form of a tension.
yeah, tension
And
and the
concrete
tension
is weak in tension, so it
is
cracks.
poor for the tension. It is good for the compression. That's why these cracks are forming inside.
Right, exactly. Concrete is bad in tension, so I mean it doesn't perform well in tension, and therefore it cracks. I mean, it cracks initially at a microstructural level, but then subsequent freezing and thawing cycles across a long duration, like let's say 700, 800,000 cycles of freezing thawing, that could lead to expansion of these cracks. And then these cracks start to show on the surface of the concrete element as well. Right? Got my point?
Yes, sir.
Yeah, all right. All right, moving on to the seventh question. In rebar corrosion at cathode met, sorry, in rebar corrosion at cathode, metal dissolves, and at anode, electrons react with oxygen and water. Is this a true or a false statement? The question is, in the case of rebar corrosion, the cathodic reaction consists of the dissolution of the metal ions, and the anodic reaction consists of the electrons reacting with water and oxygen. Is this a true or a false statement?
It is false. The rebar corrosion, cathode or anode, actually this statement is reverse, I think, isn't
Yeah,
it?
it is reversed. Yes. Right.
Yeah, that's why this is false.
Right, right. You're true. I mean, you're correct. This is a false statement. So the anodic reactions, not just in the case of rebar corrosion, in the case of any galvanic cell kind of a system, the anodic reaction is always a oxidation reaction. Sorry, oxidation reaction. So oxidation reaction is the release of electrons, right? So when something oxidizes, it releases electrons. So I have taken this view graph from the book by Mehta and Montero, and you can see over here, this is a anode on the surface of the metal. This is Fe, meaning this is the rusting or the corrosion of iron, and at the anode end, the metal dissolves to produce Fe2 plus ions, and the cathode is essentially where the electrons flow and the oxidation, the reduction reaction take place. So at the cathode, it is the reduction reaction. Oxygen and water reacts with the electrons coming released from the um, anode section of the metal. So this also releases electrons, right? Fe2 plus reduction. They have shown over here. So it releases both metal ions and electrons. And this electrons travels to the cathode end and reacts with oxygen and water. So that is the cathode process. So the cathode process consists of the oxygen and water reacting with electrons, while the anode process consists of the release of the metal ions and the electrons. So this is a false statement. All right. Moving on to the eighth question. Which of the following is required for the corrosion initiation? Depassivation, moisture, oxygen, all of the above.
All of the above, sir.
All of the above, right?
Sir, oxygen, all are corrosion initialization.
Right, yes. Yeah. So you've mentioned it rightly. All of the three components are
All of
required.
the above.
Yeah, all of the three components are required for corrosion initiation. So first is the depassivation. As we have seen in the previous picture as well, when there is a rebar inside the concrete structure, this is a rebar in the concrete embedded inside the concrete. Due to the high pH conditions inside the concrete and the what we call them as the initial corrosion products. The initial corrosion products are essentially the oxides that are formed over the rebar surface, and that act as a passivating film. So this initial corrosion products, or the initial oxide formation on the surface of the rebar, produces a passivating film. This passivating film is essential for the rebar to be protected against corrosion. When corrosion initiates, first of all, the passivating film is broken. So this could occur, let's say, in the case of carbonation, the pH inside the concrete reduces, and therefore the passivating film is broken. Similarly, in the case of chloride induced corrosion, there's a pitting action going over on the surface, and the passivating film is first broken at a given location. So this is the breaking of the passivating film, and then the ions come to this location, and that's how the corrosion is initiated. So the first and foremost requirement for the corrosion to occur is the deep passivation, or the attack on the passivating film. So this is a passivating film consisting of what we call as initial corrosion products or initial oxides. Consists of the metal oxides. Then the second and again an important parameter is the presence of moisture. Without the presence of moisture, the ions won't be able to travel, and the like let's say in the case of carbonation, even if the carbon dioxide gets inside the concrete, it won't be able to convert into carbonic acid, and therefore it won't reduce the pH, and there will be no corrosion. So, similarly, in the case of chloride-induced corrosion, for the chloride ions to travel within the pores onto the site of the rebar location, there has to be sufficient moisture for them to travel inside the pores. So moisture is a requirement. And finally, there's the requirement of oxygen, as we have seen in the previous slide as well. So all the three parameters are required for the initiation of corrosion. So the correct answer to this question is depassivation, moisture, and oxygen. All the three are required, therefore all of the above. This is concrete, and this is rebar. This is pitting. All right. The ninth question is again a data-based question. Total chloride limit for pre-stressed concrete is 0.35 kgs per meter cube, 0.4 kgs per meter cube, 0.5 kgs per meter cube, or 0.6 kgs per meter cube. Which is the correct answer? It was discussed in the lectures probably.
That is 0.4 kilogram per frame cubed. That is, as per ISA also it is mentioned like that,
Right.
0.4.
Right. As per the Indian standards, the total chloride limit prescribed for pre-stressed concrete is 0.4 kg per meter cube. Moving on to the last question of this assignment, the 10th question. Chloride threshold is dependent on which of these factors? The cement type, the aggregate type, the aluminate content, or the steel type? Which of these factors affect the chloride threshold?
This answer is exact aluminate. That is 3C3A content. Aluminate content is exempted. That is cement type, aggregate type, and steel type. That's three are included.
Right.
Accepted answer 1, 3, and 4.
1, 3,
3
and
is
4, right?
yeah, 1, 3, and 4.
Right. Yeah. Yes. So, what is chloride threshold? Can you explain? Also, can you explain how these three factors affect the chloride threshold?
This aggregate actually it is nothing to do with the chemical action. It is inert material aggregate. Cement that is chemically active, and C3A content that is aluminate. That also in chemically active, and other fourth
What
item, that's
does
steel.
how does the aluminate content affect the chloride threshold? Like what forms in the presence of chloride?
That is aluminate content means that is sulfur activation, isn't it?
Not exactly. We're not talking about the sulfate attack. I'm asking about when the in the presence of chlorides, what do the aluminates react to produce?
That is exactly, I cannot explain, sir, that
All
it
right.
is.
Okay. So, what is chloride threshold again? Can you explain at least?
That is, it is, depends upon the cover of the reinforcement, isn't it?
Um, so
For the
basically,
structure,
chloride threshold is
yeah,
the
cover
concentration of
protection.
chlorides that has to be present around the rebar region of the in the cement in the concrete for the corrosion to initiate. So the chloride threshold is that concentration beyond which there will be initiation in the corrosion. Till that amount, till that particular chloride concentration, it is okay. The rebar is still safe. But beyond this chloride threshold, there will be an initiation in the corrosion. And the chloride threshold of a given system of concrete, I mean cement and steel, is not just dependent on the chemistry or the microstructure of the cement, and not just on the steel type itself. It is a combined factor. It is a combined effect of the cement and the steel properties that result in, I mean, that produce the chloride threshold of a given system. So the first and the fourth statements are correct. Cement and steel type both in conjuncture affect the chloride threshold of a given system. And finally, C3A content. If you have, I mean, I'm not sure if it was discussed in the lecture or not, but the presence of aluminates and in the presence of chlorides, it produces Friedel salts. And when Friedel salts is precipitated inside the concrete, the chlorides that will be present in the form of ions will be reduced, and therefore the chloride ion concentration is reduced, and therefore the chloride threshold will be increased, right? So the concrete system will be able to take more chloride ingress in order to initiate the corrosion. So the threshold is in fact increased when there is a Friedel salt formation inside the concrete. So all these three statements are correct. The cement type, the steel type, and the C3 content in the cement, all of these three factors govern the chloride threshold of a given cement and reinforced concrete system. Right? So that was the end of the assignment questions of week 10. If you have any doubts regarding these questions, then we can discuss it now. Or else, if you have any doubts with respect to the lecture slides, then you can also ask them and we can discuss them. The session will go on till 8 p.m. If you have any doubts, then you can ask them. Otherwise, you're free to leave. I'll just mute myself and wait.
So regarding this corrosion, that means mainly it is rusting the steel inside the concrete, isn't it?
Yes, it is.
In, in that case, normally the volume of the steel it is expanding. In normally, how much percentage is increase the volume of the steel in that case after the corrosion and rusting and all this thing? Is it 40% or my
Um,
remembering something 40% it is expanding the volume of the steel. Is it correct or not, sir?
I don't exactly remember the number that you're asking. What is the volume increase after corrosion of steel? But it is, I could say that it is sufficient enough for, um, I mean, for it to cause signs of cracking on the concrete structure itself, on the
Yeah,
surface
yeah,
of
that is
concrete.
only. volume is increasing. That's why that tensile forces in forming inside and concrete developing start to develop the cracks and all these things. Main
Right.
thing because of the volume increase. If it is
Yes,
10 mm steel,
it is due to the
after
volume increase as well as the rust that is being formed. So the product of corrosion is a flaky material and it doesn't contribute to the strength. So the strength providing capacity of the reinforcing bar is also reduced. So your structural there is going to be a structural failure because you have already uh, you're assuming that your steel is carrying a certain amount of load, but it is not able to carry that load because now the steel has corroded, so it has lost the load taking ability. So
that means
you're going to experience a structural failure due to that and a material failure due to cracking of the concrete surfaces.
and one more thing, sir, regarding this rebar steel, epoxy coated steel also using. In that case, this is it affect anything for the bonding stress? Because in the steel,
Epoxy coated.
yeah,
Yeah.
epoxy coated steel, in that case, if it is normal steel or epoxy coated steel, which one is having more bonding strength? I mean,
Um,
concrete and
the
bonding.
the problem with these epoxy coated steels is sometimes the epoxy coating due to heat and due to exposure to direct sunlight, these epoxy coatings they become brittle in nature and they come off the steel. So that doesn't work. And when there is a deformity on the surface of the steel itself, that could induce a corrosion cell inside the concrete, right? If there is no, if there is a what to say inhomogeneity present on the surface of the steel rebar itself, that could lead to corrosion of the steel. So that is not usually recommended to be used in your concrete structures, the epoxy coated steel rebars. On the other hand, if you have galvanized rebars, even though it is costlier, uh, that is a good option to go ahead with.
Sometimes, for the seaside area and, normally using epoxy coat steel recommending, yeah, especially for the substructure structures,
Right, right.
preferring
Yeah, it is in the
for
use. So
yeah.
majorly in the case of this polymer coated composite on the surface of steel, or in the case of epoxy coated steel, we do experience this kind of brittleness and delamination of the this composite coating. And that delamination, if that is not uniform throughout the which won't be uniform throughout the surface of the rebar, so that induces a corrosion cell when you put it in the concrete. So therefore it is usually not recommended. It's not a very common way to it's not a very common practice to use these polymer coated steels, epoxy or polymer coated steel.
Polymer coating means that is a PVC, something like that, PVC.
Yes.
PVC coat. But
um,
it is not. It is, it is if it is, so the temperature changes and also it will breaking and
right.
uh,
It hardens
disturbing
and
that.
yeah, it hardens and blisters out and causes a delamination of the composite due
Once
to the due,
once it is embedded in the concrete, then it is okay. If there
then
is
it is okay.
no
Yeah, then it is okay. But while storage on the site and when in the case of normal site conditions, we won't be able to maintain uh, a good quality
uh,
for storing
and
the reinforcing bars. So when they are directly exposed to sunlight, this happens.
and the thing is, while placing, more care to be taken. Otherwise, if it is
Right.
somewhere hit and it is damaged, then the purpose will be reversed in that case.
Exactly. So it is reversed totally. Even if
Uh,
you hadn't put that composite on the surface of the rebar, you would still experience a low risk of corrosion. But now that you have put it and the surface is not uniformly coated, now it will induce a corrosion cell in itself.
yeah, yeah, exactly. It's okay, sir. It's for my side. It is okay now. I am just leaving. And then thank you for your class and all these things.
All right.
Maybe one more class will be there next weeks.
Yeah, we have another class on next Monday, and then 1 hour class on Tuesday, and that will
That,
be the end of it.
that means you having two more classes, huh?
Yeah, I have two more classes.
Because in
Next Monday
26th
we'll
of
have a 2 hour session, and next Tuesday, I mean the day after, we'll have just 1 hour session. That will be the closing
will
session.
be the final session because I
Yeah.
think 20 or 29 may be the examination. I think so.
Yes. Yes. I'm not sure about the dates, but yeah, it should be around that.
I think 26 or 29 exactly. I'm not remembering exactly, but I
Yeah. I mean.
already prepared for the attending examination. I
Oh, all right.
already registered
You're
because of
taking the exam?
yeah, yeah, I am doing examination.
Okay. All right.
I already registered, and in my case, I already attended maybe 4 or 5 courses I done for NPTELs.
Oh, okay.
Maybe during that corona period, I started to study all these
Oh,
things. In my
that's good.
case, actually, the updation only I am doing.
Uh-huh.
I am a senior citizen. My age is around 69, but still,
Oh,
for
all right.
I am
It's
just
out of your
update.
curiosity you're doing these courses.
I from the NPTEL. Actually, this is very good scheme. I don't know people how much they are participating for this NPTEL course. I don't know exactly,
Right.
but it's a very good thing doing by the Ministry of Education, doing a very good thing, and it's very good opportunity
Exposure
for the
and opportunity. Yeah.
for my side, I am just telling. In my case, it is okay just for updation and just for consultation and all these things I am doing because I
Okay.
already done 45 years experience in the construction field.
Oh my
I am civil
goodness.
engineer. I done in, my civil engineer in 1976. 1976 onwards, I was working, and most of the time I was outside India, and
Oh, okay.
mostly in Gulf countries. More than 40 years, I was in Gulf countries.
Okay.
Was in chief engineer for the construction and as the construction. I had my own construction company also in
Oh, okay.
Oman. Oman. And
Oman.
during this time, I done so many courses. Geotechnical. Also, I got the certification
Uh-huh.
and water. Last year I done waste manager and recycling. I done that is
Right.
IIT Kharagpur and digital survey GPS also I done
Oh, okay.
and soil investigation and material testing that also I done. All this I having certification. Every time I'm attending the examination also, not just attending this thing and not living like that.
Nice,
Now
nice.
this is my seventh course in
Okay.
NPTEL. I very
And
much appreciate.
you have taken the
Uh,
certification for all of these courses.
I got, sometime I am getting elite, sometime mostly I am getting 50-60% I am scoring.
Okay.
That is GPS I got, I think, elite, more than
Okay.
75%. And all my assignment also doing very, very, very good.
Nice.
And why I am saying that the new generation students, especially for these engineering students and, teaching staff, this is very good
Right. It's a
opportunity.
very good platform.
Yeah, a very good platform. This is government spending for good for us, but
Yeah.
we have to utilize. That is the only thing I have to say. Because
Right.
according to my experience, I am just saying. In
Right.
my case, it is okay. I'm just for updation, and this is I'm doing.
Yeah.
But generation students and very good course. This I am really appreciating the Ministry of Education for doing these things. And
Nice.
PD, not only that, all these are connected with IIT only. IIT, all the people cannot go
Yeah.
in
Most of
IIT.
these courses are taken by the professors of IITs.
Very good professors doing all
Yeah.
these things. You have to
And
utilize.
the initial idea was also to make the knowledge and the teachings of the IIT professors available to everyone. So
And their classes are fantastic. Some
yeah, right.
professors, very, very fantastic. We cannot get anywhere, even if it is go any other off off campus or on campus, when compared, this is very good
Yeah,
system. And
yeah,
and
very true.
yeah, yeah, and all the professors, what they are doing, very good thing they are doing for the nation.
Yeah,
Anyhow, we have to utilize. That is the only thing we have to
yeah,
consider.
yeah. Thank you for your beautiful message. Actually, the youngsters should
Also,
be learning from you.
uh, your classes are very nice, and communication also very good, and
Thank you.
audible also very good. Anyhow, right now I am just anyhow. Let us see again. Maybe
Yeah.
one or two classes. Yeah, I will be in. I will be there.
Okay.
Thank you very much. Good
Thank
night.
you. Thank you, sir. Bye. Good night. All right. Since there are no more questions, we'll close the session for now. We'll meet again on next Monday from 6 to 8 p.m. Thank you.